All right, everyone. So we are going to go over how to use the Google Collaboratory Notebook, this IPython Jupyter notebook that I've created, to extract the quality metrics from our predicted structures, right? And remember that we're looking mainly at three quality metrics. That is pLDDT for predicted local distance difference test, PAE for predicted aligned error, and lastly, we're also going to look at our MSA coverage in depth, right? So once you've downloaded the AlphaFold 2.3.1 visualization notebook, upload it to your Google Drive. You just go ahead and double click on it like this. It should launch a collab notebook, right, in a new tab. It might be in a new browser window, so make sure you check around. And I went ahead and took a wonderful script and program called AlphaViewer by Severin Dix from IBSM Freiburg. He did a wonderful job of creating this Python module that is going to do a majority of the heavy lifting for us. I only edited it a bit and then also added the MSA coverage plotting so that we had one script to do it all. But credit to Severin Dix here. Anyway, so you're going to essentially run this bit by bit. So in a Jupyter notebook or a Python notebook, you'll have text box. Like this first one's a text box. If I double click on it, you can see that there's text written here. And now that you have a copy of it, you can actually edit this as needed. I've just go ahead and placed these text boxes between the lines of code to kind of aid you, walk you through how to use it, and also explain a couple of things. So the first thing we need to do is run this first cell block. Right? This is going to do a couple of things. The first one it's going to do is actually mount your Google Drive folder. So whichever account you're signed in on Google, it's going to mount that drive as in an accessible location to this collab instance. Right? So a collab instance is an instance that's requesting computational resources from Google's cloud services. Right? And you have access to a free unit. If you go down here, over here, and click on this little symbol, you'll see that I don't pay for this, so I currently have 0 compute units available. Resources offered free of charge are not guaranteed, right? So what this means is you may expect a hiccup or two, maybe something will stop, and if you encounter that, the easiest thing to do is to go ahead and reset your session. Oops. The easiest thing is to go ahead and reset your session, and you do that by clicking runtime and restart session, right? And this will give you like a fresh new instance. So the first thing we're going to do is go ahead and run this first block. So we're going to go ahead and press the little play button. This might take a minute. It's going to make a lot of lines here. What it's doing, and if you guys remember from class, we actually had an issue with utilizing the run alpha pickle script due to these two dependencies right here. This jax and jaxlib. This was throwing an error on our HPRC cluster, and it was also throwing an error when I attempted to do it on my own. Going through various Stack Overflow posts, posts on the GitHub for AlphaFold2 and various other ways, I actually finally figured out a version of both of these that we can load into a collab instance that actually work with the output from AlphaFold 2.3.1, and that's the version of AlphaFold that we've been running in class. So a caveat, if you continue to use this visualization notebook down the road and say AlphaFold releases a new version like 2.3.2, 2.3.3, so on and so forth, you may need to mess with the version numbers of these to get them to work properly. Hopefully, as we come out with newer versions of Alpha 2.3.1, the dependency on jax and jaxlib will hopefully drop out, but only time will tell. The other thing it's doing is loading that AlphaViewer, right? Remember that great heavy lifting module from the original author. It's going to also import some other modules native to Python that we're going to utilize for plotting and accessing data structures, right? So this should run without issue. Again, if you experience any issues during execution or it throws you an error, try to restart the session and run it again. If not, go ahead and contact me and I'll try to help you through it. The next set is actually a large text block that's really walking you through how to access your data on Google Drive from Google Colab, right? So I'm not going to read this verbatim. I wrote this out for you guys to read if you're not listening to the video. But essentially, the next block of code, we have to tell the program where to find our AlphaFold2 output directory, right? The easiest way to do that is when we mounted our Google Drive onto this Colab instance, you click this little folder icon here. This window will pop out to the right, and you'll notice you have a folder called Drive. If you click on it, It's going to kind of look like Finder or File Explorer if you're on Mac or Windows respectively. And we want to click the My Drive. That's your actual Google Drive. And here's where you will need to navigate to wherever you uploaded the output directory. I'm going to use one that I did in a collaborative effort with a prior research lab, and I've stored this in a folder called AlphaFold2 analysis. So your path may differ here, just find the output directory that corresponds to your AlphaFold2 run, right? So I'm going to go ahead and navigate to mine. The one I'm going to show you is actually using the multimer model, and this is a homotetramer, right? So this is my output directory, right? If I expand it, you'll see I have a folder here called figures. You don't have that, and that's all right. But we have things like MSA, we have features.pickle, all of our PDB files, our JSONs, and stuff like that. So I'm just going to click on this folder. I'm going to right click the button called copy path, and then here, where we have in between quotation marks path to your AF2 output directory, you're just going to paste that content. You'll notice this is the full path in the collab instance to that output directory. Right, and I'm just going to hit the little play button. All it's doing here is storing this. It's what we call a string in Python in most coding languages. It's just a literal string. It's meant as this is written is how it should be interpreted, and that's being stored, or what we call cast, into the variable called path to output. Right. So I'm using this later. You'll see. Anyway, the next thing you can do is just go ahead and run the viewer code right here. This is going to run that alpha viewer program that the original author wrote, and you'll notice it's calling path to output. That path to output is right here. Right, so we're going to go ahead and run this. Right, so here's where we had that issue before where it couldn't find this JAX library. With this new version, it's going to default back to CPU as it should, and then it should run. Now, my pLDDT plot is going to look somewhat differently than yours, and that's mainly because this is a homotetramer, is the way this was run on the multimer model of AlphaFold2. And you'll notice in the pLDDT plots and the PAE plot we'll generate here in a second, when you run multimer, something that's going to look different is it's going to show you the pLDDT plot, and it's going to section them off by the chains that were supplied in the original FASTA file. So because this is a homotetramer, you'll notice that the pLDDT plots are nearly identical between, if not exactly identical, between each monomeric unit of the multimer, right? So if you have a homomer, this is what you'll typically see a pLDDT plot look like. It'll just be repeat sections of each monomeric unit, right? In this case, it's 4, right? And you can actually just save this directly by right-clicking and hit Save as Image. And it'll save it to your directory that you indicate. It's probably your downloads folder by default on your computer, but that's how you'll go ahead and save this file. You'll run the next bit of code, which is going to plot the PAE. Now, if you supply an output directory from AlphaFold2 where you ran the monomer model, not the monomer underscore PTM, just the regular monomer, it'll error and tell you that you need to check the model you're using, check to make sure you're using monomer underscore PTM. Right, as I said in class, the original monomer, just the default monomer model, does not quantify aligned error. So we have to use the monomer underscore PTM. However, if you use multimer, it automatically computes this, right? So here's a PAE plot. You'll notice this looks quite a bit different than what the ones we've seen in class, and again, that's because there are 4 identical monomeric units that make up this homotetramer. And so we have the first monomeric unit, second monomeric unit, third, and fourth across this diagonal axis right here. And then what you're seeing in every other block, right, we have 4 identical chunks, which match our 4 identical pLDDT portions in our plot above. But what we're seeing here is the cross sections between each monomer. And you can see that between the individual dimer units of this tetramer, it had higher confidence in placing the atoms relevant to the other monomer, and that's the same. So for the first 2, we see a higher rate of, a lower rate of predicted aligned error between the monomeric units in this box and this box, and then the same here for the second dimer between this box and this box. And overall, I'd say this is a pretty decent run, right? We have generally low predicted aligned error. It starts to get a little bit higher as we compare the 2 dimers to each other, or individual monomers between the 2 sets of dimers. And that's to be expected. This protein is known to be a dimer, but the particular lab of interest had some evidence to suggest that it behaves as a tetramer in some instances, and so they wanted to see what the predicted structure looked like. Right. Last one is actually going to be visualizing our MSA coverage, and this is a part I've added to the script that is not doesn't ship standard with AlphaViewer from the original author, but you just have to run this. It's automatically going to pull the features.pickle file. This features.pickle file is actually what contains your MSA alignment, depth, number, all that fun stuff. So you should just click this. It should run pretty quickly. It's also going to go ahead and save the figure in the output directory. You can also just right click it here. So again, this is another MSA, and you'll notice it's also got a unique profile. Just like the pLDDT, right? We see repeating sections of the graph for each monomeric unit in the homotetramer, right? And so you can look at this. We had about 2,000 sequences that align to our target. And you can actually see what's quite interesting here is that the MSA coverage almost mimics the pLDDT plot. Not exactly, but it has the same overall shape, right? It increases and stays pretty high in the middle of each monomer, and then sinks back down towards the C terminal. And this is, or C terminal, sorry, yeah, that's right, C terminal. You can see that this is pretty standard, and so actually what we really like here is the fact that we had high sequence depth coverage across nearly the entire amino acid sequence. And this is really what we would like to see, right? So yeah, that's it. That's running this little visualization Jupyter notebook in Google Colab. So if you guys have any questions, please email me or set up an office hour to come talk to me, and we'll go through it together. All right, I will see you guys in the next video.